Okay, we're at 9 o'clock. As people trickle in, they might miss a few slides, but that's okay. I think we have quite a bit to cover this week. We're going to go over what we were not able to fit in last week, which was basically a look at how to compare response rates between groups, and then we'll get into regression methods like linear regression, logistic regression, and survival analysis. As a reminder, these lectures are being recorded and posted online for viewing. Remember last week we covered different methods for comparing a continuous outcome between groups, in other words, for comparing means, mean responses. And we talked primarily about the t-test and analysis of variance, or ANOVA. The t-test is appropriate when you have one or two groups. Analysis of variance is only appropriate when you have more than two groups. T-tests should not be applied in that case. Today we're going to cover a similar concept where we're comparing, instead of a mean response, we're going to compare rates of success or rates of response between groups. So for instance, the outcome here, or the group summary, would be like a proportion or a percentage. And so what percentage of patients are responding on treatment A versus on treatment B. The primary approach to that is using chi-square tests, but there are other options, which we will see when we get to regression methods, where we may employ something like logistic regression instead. So here's a quick example where we may be interested in comparing response rates between groups. Notice here that I'm summarizing the data in a contingency table form, because whereas prior we had groups and we were comparing their average response, now we're comparing a categorical response between groups, which is why we end up with proportions. This is a very common comparison in cancer research, where we're interested in how patients are responding to competing treatments. So here we have two treatments under consideration, A and B. One of these is a control, one of these is experimental. And the response here is on an ordinal scale, from basically treatment failure, which is F, all the way up to a complete response. And there are metrics for classifying a patient's response into one of these categories based on the change in their disease, the radiographic visualization of their disease from baseline to some follow-up. So obviously a complete response is the best kind of outcome here, and a treatment failure is the worst kind of outcome. And an investigator is looking to see whether or not the way patients respond is independent of treatment, or is there some association with treatment. So that's all that this test is looking at. It's looking for an association between two categorical outcomes. And we tend to report data like this in a contingency table, so you see the frequency or the number of patients who received treatment A who had a complete response. And that was 32% of individuals who received treatment A were able to achieve complete response, compared to 9% in treatment A who had a failure, a treatment failure. And then we can look again, 27.5% of patients who received treatment B and 8% who received treatment B had a complete response or a treatment failure, respectively. So the idea here is we can visualize this, but we want to know, are the patterns of response rates different between the two groups? It might get to the effectiveness or the relative difference between the two treatments. And this, by the way, is called a chi-square test of independence. There are many chi-square tests. This is a specific kind. Just like with the T, though, what the chi-square statistic, it's another test statistic like the T. It's going to be comparing what we would observe, what we actually observed in the data versus what we would expect to see in that contingency table if there was no impact of treatment on response. So we should see similar response rates in the two groups. So it's just comparing, again, what we observe to what we expect. With the T, we did that by taking the sample mean and comparing it to our hypothesized mean. And we took the difference between that and we standardized it by a measure of the variability in the data, or the sampling variability. We're doing the same thing with the chi-square statistic, except now we're comparing a response rate that we observe to a response rate that we would expect if there was no association between treatment and outcome. And then we have to average that over all of the different possible combinations of outcomes. Just like with the t-test, it had an assumption that the data was approximately normally distributed, and if you were doing more than, you're doing a two-group comparison, you had to have equivalent variance or variation in the two groups in order for it to work appropriately. With this one, the only assumption that you need to verify is that you have a sample size large enough, essentially. The sample size has to be large enough so that the counts, the observed counts, like this 32 and 55 and 16 and 9, none of those can be less than 5. So it's essentially related to two things. It's related to the rate that these different types of responses are occurring and your overall sample size. So if you end up with a really small cell count, you probably shouldn't do the chi-square test because it may give you incorrect inferences. You can use a Fisher's exact test instead. Fisher's exact test is a non-parametric method that has no assumptions that can be used on contingency table type data. So again, we hypothesize that response is independent. Well, the scientific hypothesis is that one of these treatments is better. So the response is a function of which treatment these individuals are getting. They're not independent. So in order to test this hypothesis, we have to set up the null hypothesis, just like last week, and we state that it's independent of treatment. In other words, let's show that what we observe is different from what we would expect if the response is independent of treatment. And if those are big enough in terms of their difference, then we can reject the null and support somewhat indirectly our scientific hypothesis that the treatment, there is an actual treatment effect. So that I just summarized that. So to do this, again, the chi-square test, just like with the t, it has degrees of freedom. The degrees of freedom are related to the size of the table, the number of rows and columns in the table, details that are not necessary for you all to be able to interpret or even perform the test necessarily. But the chi-square test can be done in RStudio very simply. Just like with the t-test, there's a function called CHISQ.test. You can pull in a data set using Excel and indicate which variable is treatment, which variable is response. Or you can actually, if it's a small enough set of data, you can type in your treatment, A or B, and again, a record for each subject, and then the response of each subject, complete, partial, failure, so forth and so on. And then if you plug this into whatever tool you're using, you'll end up with a p-value, a chi-square test statistic that's 7.815. And I'm not going to go into the details of the chi-square like I did the t. Just understand that since the chi-square is a squared value, it cannot be less than 0. So what you end up having is, it looks like someone took the t distribution and folded it over on itself. And so all of its area is above 0. So areas in the chi-square values that are very large, just like with the f, indicate association. They indicate that what we observed is very different than what we would have expected. So in conclusion, since we have a large chi-square statistic, and again, this is equivalent interpretation to the t, and a p-value that's relatively small, we can reject the null hypothesis and state that it does appear that there is some relationship between how patients are responding and what treatment they get. And in order to really understand what that relationship is, you would then, there are, again, just like with ANOVA, some post hoc methods. You could report estimates of the different rates and confidence intervals. You can report them in a graphical form. So I have treatment A and B indicating our groups, and then here I have the percentage of patients who received that treatment who achieved a particular type of response. And it doesn't, unfortunately, project well here, but what you can see here, this is the best possible response. It's in B, and the best possible response in A. So we have 27.5% versus 32%. It appears where the biggest difference is occurring is the difference between partial and stable disease. We get a lot more individuals on treatment A. If you kind of lump together complete and partial responders, there's many, many more. In fact, it's 75% of patients achieve some kind of response versus 59%, 60%. So that's probably, again, it would require this additional investigation to really describe what the effect is that we're observing and why we ended up seeing some kind of association or difference between the two treatments. This is a very common technique. So we talked about how to power a t-test last week. Let's talk briefly about how we power a test when we're comparing response rates. It's a very similar process. We still have to have an effect size measure. So what difference do I really want to detect? We have to have a type 1 error rate specified. We have to have a power, a minimum amount of power specified. And then a combination of those things will get us to the required sample size for achieving an objective. So here's an example from 1978 where they do a randomized double-blind trial comparing a treatment versus a placebo in patients after myocardial infarction. So in order to power a study like a randomized controlled trial, we have to understand, we have to identify the answers to each of these questions. What's the purpose or the goal or objective of the trial? In other words, what's the hypothesis if we're doing a test? What's the principal measure of patient outcome? So that's the data, the endpoint, the outcome that we're going to be comparing between groups. How will the data be analyzed? So what's the statistical test that we'll be performing to compare the treatment groups or to detect a treatment effect? What type of results do we anticipate with the standard treatment, with the control? So that's kind of like where we exist in terms of baseline comparison. And then what's the minimally important difference to detect before we would push this forward and say this treatment appears to be effective? So the primary objective in this study is to see if the treatment is of value in preventing mortality after MI. The primary outcome, the measurement that we're taking on each subject, is treatment failure, which is indicated by death within 1 year of their first treatment. And so the way that this is going to be coded in the data is if they have the event, in this case death within 1 year, we're going to code them as a 1, which is like a yes. And if they are still alive or surviving at 1 year, they're going to have a 0, which means that they did not have the event. This is kind of setting us up also for thinking about how we would maybe do this from a survival analysis perspective. The difference between what we're doing here and what we would do in survival analysis is we are not incorporating the time to death. We're only recording whether or not that event occurred within 1 year. Notice the differentiation here between what we're seeing now and what we saw last week is this is binary data or categorical data, outcomes that are not continuous. And so that would require something other than a t-test. The data analysis approach commonly applied in this case, if we're not going to adjust for any other factors, would be a chi-square test if we have a sample size that's large enough, because we're really interested in comparing the percentages of patients dying on each of these, the treatment and placebo, within the first year. And so I'm going to indicate that by two different metrics here. P1 is the percent on the treatment, P2 is the percent on placebo. And we're going to assume the 5% level of significance. So we don't want to make an error. We want the chances of making a false rejection or a false positive in this case to be less than 5%. We also have to define what the expected results are under our control. So we've been observing patients in this circumstance for a long time. We kind of know the rate at which they're dying within a year. Either we know it from observation or it's been published. And so the investigators here expect about 10% of patients who remain untreated to, and when I say by untreated, I mean without this drug intervention, to die within a year. So that comparison rate is about 10%. Notice we're making this assumption, we're not observing it. What we actually observe in our control group could be very different from 10%. That's why we have to always be careful about keeping those kinds of things in context. The clinically interesting difference we want to detect is whether or not this intervention can cut the mortality rate in half. So if, again, we assume that 10% of patients die when they receive placebo, we would hope to achieve a mortality rate of 5%. We want to cut that in half. Now, it doesn't have to end up being a 10% and 5% exactly in our data in order for power to still be achieved. But we do need to see at least whatever we observe in the standard of care, or the placebo in this case, we need to see half that in the treatment group in order to have adequate power. So in English, it's our goal to identify a treatment that decreases the 1-year mortality of patients to no more than 5%. And we would like to be 90% sure that we can detect this difference if it in fact exists. The 90% is the power of the test. So again, we have to set up our hypotheses. Our null is that the two rates are equivalent versus not. Notice I'm doing a two-sided test because I want to know there's a possibility here that whenever I give this drug to patients that I actually increase the rate of mortality. And so I need to be able to detect that. So it's a conservative approach. Type 1 error rate of 5%, power of 90%, and that difference between the two response rates needs to be at least 5% before I want to flag this as statistically significant. The power for this test, again, can be computed. There are many tools online, but there's a function in RStudio called power.chi-square.test. Notice power is not spelled out. Okay, I'm not sure what this is. Let's see. But we also have to use these two functions, which are basically effect size calculators. The effect size calculators compute, again, this measure of effect size, which is W. Sometimes you hear it called omega in places. But regardless, notice here, actually, what we're computing is what looks like a chi-square statistic. It's taking the difference between what we would expect and what we hope to achieve under the alternative hypothesis. So, for instance, I will have to specify under the null, and I apologize, this is not very big, under the null hypothesis that they're equivalent, then what I would expect to see would be 10% and 10% in the two groups. Under the alternative, I expect to see 5% and 10%. And so you don't have to calculate this measure yourself. RStudio will do it. Maybe some other software will do it. And it computes this Cohen's W effect size just by plugging it in to this es.w function. And again, specifying your expected response rates under the null and the alternative. It will allow you to use the chi-square function. If we were to compute this, the measure is actually, omega is W is 0.158. And there, again, Cohen likes to give us these kind of rule of thumbs to tell us whether this is a small, medium, or large effect. And it turns out what we're looking for is a small effect. So it turns out that most effect sizes in medical research are small effects, which is why it's sometimes hard to detect them. We tend to make baby steps as opposed to major breakthroughs. So at least we're going in understanding that the potential here is that we have a small effect, but it's still meaningful or important that we are able to detect it. So to power this study, we plug in, again, we've used that effect size measure to compute the effect size, and then we can compute the required sample size using that power.chi-square.test function. So the things that you have to give it the significance level, which is the desired level of significance. your desired level of power, and then degrees of freedom here, again, are the number of rows in your contingency table times the number of columns, each of those minus 1. Rows minus 1, columns minus 1. So for our contingency table data, our rows would be the treatment groups. So we basically have 2 treatment groups minus 1. So that's the number of, that's one measure of the degree of freedom. And the number of columns is whether or not they respond. So the number of columns in a contingency table here is 2 minus 1 gives us 1. So row minus 1 times column minus 1 gives us 1 times 1, which is 1. Again, probably overkill on the details, but if you wanted to be able to use this, you need to understand at least that feature of the chi-square test. Yes? You can actually, so this study may have had unequal sample sizes. I believe, I don't know if this particular function allows you to have anything other than 50-50 randomization, but there are other functions I think that do. Probably if you wanted to determine, maybe the optimal allocation to groups, you might need to try a test that's a little bit more powerful. They're actually, and I'm kind of speaking here without remembering what all the capabilities of this particular test, but there are functions that for instance, you can tell it, don't restrict it to just equal group sizes. Give me the optimal scenario, the total sample size, and maybe how many go in the treatment, how many go in the control for this test. Because yes, you're absolutely right. 50-50 is not always optimal, especially when you get more than 2 treatment groups. So here, again, just putting in the omega, or the W, I keep calling it omega, the W that was calculated by that effect size measure, which again kind of summarizes what effect we're looking for. The degrees of freedom of the test, the alpha and the power. We can see here it spits back out all of your inputs and gives you the number of observations required. So the number of observations required for this study, number of subjects required is 420.2, and we always round that up. So 421. Notice this is based on a mathematical formula, so you actually will probably need to use or enroll more than 421 subjects, especially if you're going to try to achieve balance between your groups. And then we often try to account for attrition or, loss to follow-up, that kind of thing. So if you anticipate you're going to lose 10% of the study subjects before a year, in other words, you don't think you'll be able to record their survival, then you would want to over-enroll to make sure that you achieve at least 421. So here, if I were, again, putting this into a protocol or a grant, I would need to describe exactly how I came up with the estimate of the sample size. And so an overall sample size of 420, this should be higher than that. We, again, need to account for attrition. It would provide us with 90% power to detect a 5% reduction in 1-year mortality using a chi-square test. Assuming, again, you need to be transparent about all the things that you assumed. That way, the person who's reviewing your protocol or reviewing your grant can make sure that the assumptions that you made are feasible. Any questions about the chi-square test? We can get into survival analysis. Let me make sure that we don't have any questions online. Doesn't look like we do. No, that's just for this particular study. So yes, so you might want to detect a 20% difference. 20% is actually very common. But again, in this case, only 10% of patients are dying within a year, so a 20% difference isn't even possible. Depends on what your outcome is and what you're actually trying to achieve. Yes. So here, yes. You do need, yes, all of these tests that I've gone through so far require independence. In other words, I haven't done anything here where we have repeated measurements or measurements taken on the same subject or naturally paired or matched data. The methods become a little bit more complex aside from like the paired t-test, which is pretty straightforward where you have like a pre-post comparison. Can you think of a scenario where you might have something like this, where the data would be matched or paired or dependent? The response? Yeah. Yes, so there are methods for, if you're doing a longitudinal study, there are methods for modeling a person's response, whether it be binary or ordinal, over time. And those tend to come in more complicated models where you have effects that account for the fact that you're repeatedly observing this particular patient. So their outcomes are likely to be more correlated than outcomes with other people. I can tell you in practice when I'm designing a study, we tend to simplify. We still do that analysis, but our primary goal is usually we pick a primary time, a primary follow-up point, like a year or 6 months or 4 weeks or whatever is most meaningful scientifically, and then we focus powering a study on that time point. Even though we will do the data analysis later, taking into account the entire kind of trend or pattern of response over time, we tend to just pick a single one. Another one which is similar to what we had for this complete partial stable failure is in cancer studies we observe a patient's response many times over the course of a study, but very often we hypothesize that their best response achieved is different. So for instance, a person who achieved a complete response who ends up here might have eventually had a treatment failure during the study, but their data contributes here because I pre-specified that I wanted to see what's the best response achievable in patients under these different treatments. And so, there's some complexities. It really depends on, again, what the investigator thinks is meaningful to address. And we can even get more complex than that by having, there are models and methods that we have now that will allow us to detect simultaneous improvement in both survival and quality of life. There are methods for doing that simultaneously. Because what you don't want to happen is you're improving survival, but their quality of life is bottoming out, because that's not necessarily for 100% of patients what they're after. So it allows us to describe the overall patient experience in terms of how much longer they're able to live with the disease and their quality of life while under treatment. And again, really the sky's the limit with the kinds of questions that you can ask about an intervention. There are methods that either are developed or can easily be developed. I don't know about easy, but can be developed to address the question. So speaking of the study of occurrence and timing of death, survival analysis is a generic term that we use to discuss this kind of class of statistical methods that studies not only whether or not an event occurs, but its timing of occurrence. So did it occur within 4 weeks? Did it occur within 6 months? Did it occur within a year? So this type of analysis is different than what we just saw. We're still including whether or not an event occurred, response or non-response, death or survival, but we're taking into account in the data analysis the time at which we observe that event occur. And we call it survival analysis, but this is applied beyond even medical research. It's applied in risk assessment in setting rates for insurance policies. How long can I expect an individual with these characteristics to not actually submit a claim on their policy, for instance. Could help set the rate for that. So the event really could be anything where you're interested in both whether or not it occurs and the timing of its occurrence. So that could be the development of a disease. And that would, again, be a question in perhaps like a cohort study, where you're identifying a cohort of individuals who had an exposure, and you're following out to see whether or not they have the development of a disease. Response to treatment, relapse or progression, death, rehospitalization, any either positive or negative outcome that's of interest to you, where it's important to not only know whether or not it occurs, but kind of when it's occurring over time. For us, again, survival analysis is most commonly applied to the study of deaths, but I've got an example in here where the event is not necessarily death. It's, for instance, a major cardiovascular event after some kind of an intervention. So some of the important aspects of survival analysis include the survival time. Survival time is the time from some well-defined origin, that could be the initiation of treatment, the diagnosis of disease, randomization, whatever, to the occurrence of the event. So the occurrence of the event, the timing of that is the end time. And then the data set that we tend to work with includes the time, which is the difference between the predefined origin and the occurrence of the event, whether or not they had the event. So that's their event status. Some individuals will not die during the study, and so they're what we call censored. You don't actually observe what their time to death is on your study. And then when we do regression methods, we might want to have other relevant subject characteristics that could be prognostic for the event occurrence. In most clinical studies, the length of the study period is fixed. So when we get a grant, or we pre-specify in our protocol that we're going to do this study in 2 years or 5 years. The length of the study period is fixed, and the patients enter the study at different times. So because of that feature in clinical investigations and some other things like loss to follow-up and not being able to observe the event, we tend to have what's called incomplete or missing data. This is a unique kind of data in survival analysis that's called censored. It's censored data, and all it is truly it's missing data. But we have methods to take into account the censoring. Very rarely do we have complete data in clinical investigations where we do survival analysis, unless it's one of those really long, like 10-year studies, and we're able to see every individual in the study develop the disease, or we're able to see survival times for every individual under study. And again, censoring is a unique form of missing data. Here I'm showing you 4 different study subjects and whether or not they're censored. So assume we have our time origin here on the left. And again, this in actual time occurs at different points for different people, because patient A is not necessarily diagnosed, if that's the origin, not diagnosed on the same day as patient B. One might have been diagnosed a year ago or 6 months ago, and B is more recent. But we standardize them all to an origin time, and then we count either the number of days or months or years until we observe their event, or until the end of the observation period, which is we'll call the end of the study. So for patient A, we actually were able to observe them the full length of the study period without them dying. So what they're contributing to our information is 12 months of survival, and then they're censored. So we did not observe the event, even though the event, notice they did actually die, but it was after the study ended, after the period of observation. So we can't incorporate that information into our data set because very often we don't know what happened. Patient B, we observe their event prior to the end of the study. In fact, they died at 11.6 months, and so they were not censored. We actually observed their complete data. Patient C, The difference here is I observed them for 9.5 months about, but then I lost them. I don't know, they quit coming back. I searched through maybe, different sources of data where maybe I could try to find out whether or not they died, more public sources of information, and I can't find anything about them. So all I know is the last time I saw them, they were alive, and the last time I saw them was at 9.2 months. So I record their time, their survival time is 9.2 months, and then I censor them to lost to follow-up. And then D, similar to A, notice although A had the event and D didn't, they end up contributing the exact same information to the data set. 12 months and censored. Even though D didn't have it and A did, they were both outside the study period. So this is a unique feature of survival analysis that we have to account for when we're following individuals for the event. So the functions of survival time that are important to understand: the survival function, which is what most people report through a Kaplan-Meier curve, is just it describes the probability that an individual will survive up to a given time point, given the type of treatment or exposure that they have. And so here's actually what the survival function is telling us. It's the probability that an individual survives longer than time t. To read this, notice at the beginning of a study, at time 0, 100% of patients or subjects on these two groups are alive. When we start to see dips or drops in the function, that corresponds to observed events or observed deaths in that treatment. So the more rapidly this function is approaching 0 on the y-axis, the more rapidly this event is occurring in that population or in that set of subjects receiving that treatment. Notice here, I can see that the rate of descent of this function is much greater. Not only is it starting earlier, but it's kind of, because it gets that head start, it's maintaining some distance from the other treatment group. So I would say that the survival, the pattern of death, or the risk of death, is higher in this group represented by the dotted line relative to the line that's solid. If I were to do a test to actually compare these two survival functions, I would get a p-value from the log rank test of 0.01, indicating that there's some difference here. And a difference that you can see is obvious. Another nice thing about the Kaplan-Meier curve is that you can estimate median survival. In other words, what's the time at which we can expect 50% of patients to still be alive? So if I think about 50% of patients, that's where the y-axis is about 0.5. In order to figure out the time, the median time, which very often, again, we get from numeric summaries, but we could also visualize it. You just go out to each of the functions, and where it crosses the 50% threshold, you take a look at the time. So it's just a little over 18 months. 50% of individuals survive beyond 18 months in this treatment, compared to 50% of individuals survive almost 30 months, if I'm drawing my line correctly, a little bit less than 30 months in the competing treatment. So lots of different things that you can say just by visualization of this survival function. And again, this is generated by a Kaplan-Meier method, which is an estimate of the survival function. Another function of survival time is the cumulative incidence, which I'll talk again about in a little bit. Or you sometimes hear it called the cumulative hazard, cumulative risk. And it's describing, kind of in an inverse way, the incidence rate over time. So whereas before we were describing the percent of patients who are event-free up to a given time, here we're describing what fraction of patients have had the event. And so you can see that this is an increasing function. We'll take a look at this inset because it's easier to see. An increasing function. So the faster it's growing, the more frequently this event is occurring earlier. And we see a little bit of deviation between the CPAP and usual care here, but potentially not enough for there to be a statistically significant difference between the two. The hazard function, and I talked a little bit here about incidence or hazard. The hazard, this is directly related to that. It's a function of the survival time. So it's related to the Kaplan-Meier curve. It's related to that cumulative incidence. But the hazard function is describing what's called the conditional failure rate. It is, rather than the probability that a patient will survive up to a time t, it's describing the probability of a patient having the event during a very small time interval. So the way that I would interpret this, if the study time is described on the x-axis and the hazard is described on the y-axis, time goes from baseline to infinity here, and then the hazard goes from 0. And again, increasing hazard means kind of increasing risk of having the event. Notice if we take a look at the green function, that if this is describing the hazard for a set of patients, these patients are at high risk of dying very early, and their risk is decreasing over time. This is describing the risk of the event at that time point. It's a little bit different than the survival function. So high risk early, low risk late. The red is the opposite. They actually have very little risk of having the event early, but that's increasing over time. Maybe the treatment quits working, or the disease, just because of its nature, eventually these individuals die. Another interesting shape that we often see in hazards is what's called the bathtub shape, which you kind of have a mixture of two populations here. Individuals who are at risk early and individuals who are at risk late. So individuals are either dying early, their risk of death decreases, but then at some point starts to increase again. That's the bathtub shape. You often don't see the hazard plotted out like this, but it is describing the instantaneous risk of the event occurring. What's interesting is how we interpret the hazard. The hazard, again, corresponds to the risk of the event occurring at time t. For example, if I have I'm doing a study and I'm measuring through survival analysis techniques influenza, cases of influenza, and I calculate a hazard in this population of 0.015. So I could state in English that a patient's hazard or risk for contracting influenza is 0.015. And it's important that I know that time here is measured in months, because the unit of time tells me how I could modify this hazard estimate to something meaningful, because that makes absolutely no sense to me. I could multiply, since this is in months, I could multiply it out to, so times 12 would give me the hazard in a year, and then times 10 would give me the hazard in a decade, which makes more sense because not everybody's going to get the flu every year. If it's something that occurs more frequently, we might only need time measured in months, but here we need it in decades. So if I multiply this out by 12 months, I can get the hazard or the risk in a year, and I can get it in 10 years if I multiply that out by 10. So doing that would give me something much more easily understood. The patient or a patient would expect to contract influenza twice in 10 years, assuming their risk remains constant over that 10 years. There may be things that would modify their risk of influenza, which would then mean that it wouldn't make sense to summarize their overall risk in a decade with a single number. You might want to actually plot out their risk using a hazard function, if it's increasing over time or decreasing over time or bathtub shaped. So that's the purpose of that, is it's a way to describe risk either over time or within a specific unit of time. Methods for comparing survival functions include probably the most commonly applied method, the log rank test. You also see variations of the log rank test that allow you to give more importance to either earlier differences or later differences. The important thing to understand about the log rank test is that it's taking the entire observation period all into account in an equal manner. So this is actually best when you see a difference early and you maintain that difference over time. So you see an early separation in Kaplan-Meier functions and they stay apart over time. But that's not often the type of difference that we see. If we see a different kind of difference, for instance, we might see a converging set of Kaplan-Meier functions. Notice we have separation early in this middle graph, and then by the end of the observation period, they're actually identical. They come back together. That's called converging. It's an early difference that fades. We might also see it at the opposite, which is diverging, which is kind of a long-term benefit, which is on the far right here, where for the first period of observation, they're equivalent. And at some point, then you start to see the benefit kick in. Here we see that risk of death flattening off in the gray, and that's a diverging. The two things that we have here in the middle and on the right are what are called, there's not proportional risk. In other words, the difference in the risk of the event between the two groups changes over time. So it makes sense then to describe how that risk between the two, the difference in the risk between the two groups is changing over time, as opposed to trying to summarize it with one number, because that might actually underestimate or overestimate the difference between the groups. You'll hear a lot of times when we do survival analysis that the methods that we're using assume proportional hazards. When you say, I'm assuming proportional hazards, you're saying that the treatment effect, the risk of the event in treatment A versus the risk of the event in treatment B, that difference is observed early and it's sustained for the entire study period. And that's a pretty strong assumption to make, which is why, unless you have a very large benefit, sometimes the log rank test won't show it to you statistically. That's also why when we do Cox regression, notice part of the title of Cox regression is proportional hazards. That's an important assumption to make. There are other methods that account for diverging or converging survival functions. But I've given you here a couple of very similar methods to the log rank test, which by the way is a non-parametric method, that if you know before you do the study, and again, just like with everything else, we cannot let an analytic method or the analytic plan be a function of the data. The analytic plan has to be pre-specified. Otherwise, the p-value that you get out, you've completely invalidated it if it becomes random. If it's a function of the data, then the analytic plan is also random. And the p-value no longer represents what you think it represents, which is the sampling variability. But here, the Wilcoxon test, which is just a variation of the log rank test, instead of weighting differences over time and assuming proportional hazards, it actually gives precedence to early effects. So this is better for detecting those short-term differences in survival. Something like this one, where you see the benefit early and then it might come back together at the end. The Fleming-Harrington method is a method that you can actually set the weights yourself. If you think the difference is in the middle, if you think the difference is at the end, if you think the difference is at the beginning, or if you think it's proportional. So Fleming-Harrington method is actually the most flexible of all of them, where you can narrow down on a particular time where you think you're going to observe the biggest effect. And the key here is understanding, maybe what you can anticipate, what you expect to see in terms of the survival. If you don't know what to expect, the best approach is the log rank. The best approach is assuming proportional. because that does give you kind of an average effect over the entire study period. But if you know what to anticipate, you could actually have a more powerful test by modifying your analytic plan. Another common method for comparing survival functions, or at least describing the difference or the treatment effect, is the hazard ratio. The hazard ratio is very similar to an odds ratio, and I'll show you in a moment how you would interpret an odds ratio versus a hazard ratio if they're the same value. The hazard ratio just represents a ratio of the risk over a well-defined period of time. So if I'm following individuals for a year, the hazard ratio is a single number that represents how much more or less likely the event is to occur in the exposed group, like the treatment group, relative to the control. So here I have a table, again, that corresponds to that CPAP study that we saw earlier with the cumulative incidence. Notice that the primary endpoint here is major cardiovascular events. And so they have summarized the number of events and the percentage of individuals in each of the groups who had the event. There's the CPAP and the usual care. And they describe that effect, that treatment effect, using a hazard ratio of 1.1. And they give a confidence interval. So just like with any other ratio, a value of 1 means that the risk in the two groups of the event over that time period is the same. It's equivalent risk in both groups. If I have a hazard ratio that's greater than 1, I actually have increased risk. If I have it less than 1, I have decreased risk. So here, a hazard ratio of 1.1, the meaning of that is that we estimate that the rate of the event is 10% higher during that period of observation in the treatment group relative to the control. It's not much higher, but 10% might actually be meaningful depending on the clinical application. The p-value, and this was this study itself was designed for this primary composite endpoint. The p-value here is only 0.3, so it's not statistically significant, but at least you're also recording and reporting what the effect size is that you observed. So most people are familiar with odds ratios and hazard ratios, but what is their difference? So odds ratios, again, it's the ratio of the odds of an event occurring in the treatment relative to the control. The hazard ratio is the risk or hazard. And these mathematically have a slightly different meaning. The interpretation, if both of these have a value of 2, for the odds ratio, we can say that death, or the event, is 2 times more probable in the treatment group compared to the control. For a hazard ratio, we can talk about the frequency of occurrence over a time period. So let's say that this is measured over a year. Death will occur on average twice as often in a year in the treatment group compared to the control. Let's take a look at an example worked through for survival analysis. Here we have a type of cancer. This is an observational study, by the way. This is not randomized. It's a pilot that they went back and took a look at medical records to see whether or not individuals who received an accelerated radiation therapy had any better outcomes, survival outcomes, versus those who received that standard radiation therapy. The researchers here are interested in exploring any differences in survival between the patients in those two groups. So the table to describe this study is given here. I've got the accelerated group on the left and the standard group on the right. It's important that we describe all of the different factors that could play a role in how a patient responds to treatment. So gender, age, the site, the primary site of the tumor, the stage of disease, and the stage of the tumor are all described here. One important thing to notice that we'll actually look for in a moment is notice the stage of disease for those who received accelerated versus those who received standard therapy. Those who ended up getting, using clinical decision-making, the accelerated treatment were more frequently, they had a higher stage of disease more frequently. They also had a more frequently a higher tumor stage. This makes sense intuitively and just demonstrates the problem with these kinds of observational studies. If at the end of a comparison between the accelerated and standard group, we see a difference, is it attributed to the differences in treatment? In this case, it makes sense that people with more severe or more advanced disease are also getting the more advanced or accelerated or intensive treatment. So that could actually mask an effect, because if people who are sicker are getting a better treatment, they still may not, it might not show a treatment effect because you're comparing apples to oranges, if you will, in this case. And we'll see that in this data analysis. Let's just take a look at the Kaplan-Meier curves for the accelerated versus the standard therapy. Accelerated in blue, standard in red. Notice that they actually cross. They cross at 6 months. There's a little bit of separation, but they come back together. So it's not surprising that if we did a log rank test, which again is assessing whether or not there's an overall difference in the entire study period in survival, that we don't find anything. The accelerated therapy results in a median survival time of a little over 18 months. The standard results in a median survival time of a little over 13 months, so about a 5-month difference, but no overall survival benefit according to this test. But again, this is an observational study, and we have some things that we need to account for. We can stratify. That's one way to account for a confounding variable, a confounding factor. In this case, the severity of the disease is a confounder here. So we're going to account for that by stratifying on stage. We're going to further subdivide these two groups into individuals with stage 3 disease and stage 4 disease to see whether or not one of these subgroups is actually showing a benefit, or maybe a comparison within stage of disease would actually show some kind of benefit. So now we've got 4 functions as opposed to 2. The accelerated group, stage 3 and 4, that's represented by the red and the green. The standard therapy is represented by the dark blue and the light blue. Notice that those 3 groups, which is basically all standard therapy, all patients who receive standard therapy, and those who received accelerated therapy but were stage 4, they all have very similar survival patterns. In other words, they're dying early, and the risk is very high early on. It's the worst in the standard therapy for stage 4 disease. We do see that the individuals who have stage 3 disease who received accelerated therapy, they're not dying. The risk of death is actually lower over time, because we see that they don't observe the first death in that group until 24 months. And it's very stair-step because there's only, I think, 4 patients in that group anyway. So again, it's important. Again, this shows kind of one of the features of observational data analysis, in that you have to sometimes stratify and dig down into subgroups to really understand the pattern of response, or the relationship between treatment and control. That doesn't mean that this is a definitive result. It just means that there's evidence here, and we probably need to take this into the only kind of study design, if it's ethical and feasible, that can actually identify that causal relationship, and that's the randomized controlled trial, which minimizes the impact of confounding and other things on the outcome, on the treatment comparison. The p-value here is 0.0792, which is highly significant in this kind of study, highly significant. And we can also see that there's evidence of prolonged survival by looking at the summary of the median survival times. At stage 3 for accelerated therapy is almost 80 months. No other combination of stage of disease and therapy results in survival of over 20 months, median survival of over 20 months. Because it's small. I mean, 0.05 isn't a magical cutoff. That to me is evidence that there's something here. This is an observational study. I'm putting people into really small bins, which impacts my power here. So this tells me that I actually have a pretty pretty good evidence that this needs to be investigated further. This is not saying that accelerated therapy is superior in any way. It's saying there's evidence of it being superior in people with stage 3 disease, and we need to investigate this in a randomized controlled trial, or at least in some kind of design that improves the strength of evidence of this result. This is also a reason why 0.05 is not, we can't live and die by that. If I were doing this study, I would probably, in an observational study like this, I would say I want to see a p-value of 0.1 or less. Because what I'm doing here, the consequence of me making a false positive decision would be that I waste some time and resources on a randomized controlled trial. But the consequences of not achieving 5% significance here and actually abandoning this could be that I'm not going to contribute to the knowledge of science in this area, and I might actually miss an effective treatment, which would really only be identified through a large randomized controlled trial. Any questions about, we're going to come back to survival analysis in a moment, but I want to get into regression. We'll talk about Cox regression. So regression methods are typically employed when we're doing what we just did. We're comparing responses between groups, whether that be mean response or response rates or survival between groups. But we want to adjust for other factors that are usually either what we think may be confounders or prognostic for outcome, which means that they impart some effect on the outcome, and we need to take into account their impact when we're estimating the treatment effect. There are different kinds of regression models that we employ. The one that most people are familiar with is the second one here, linear regression. And that's when we're doing any kind of association between predictors and outcomes when the outcome is continuous. But we can actually use linear regression when we're comparing means and we're adjusting for, say, the patient's age in the analysis. Logistic regression does the exact same thing, only we employ that when the outcome is no longer continuous and we're comparing maybe response rates between groups. ANOVA models are regression models. So I actually didn't even have to show this because they're doing the exact same thing. They're specific types of regression models that occur when all of your predictors are categorical. So you tend to see that when you have, you've got 3 groups and you're comparing a continuous response, which we've actually already seen. There are many variations on ANOVA. I also showed that table last week. But just know that these are just regression models. And you can do any combination of different types of predictors. What's really important is whether or not your outcome, your Y in your model, is continuous or categorical or a time to event outcome. And that would be when we would use something like Cox regression. Let's start with the one that most people are familiar with. That's linear regression. And that involves looking at relationships between variables, x's, if you will, and y's when your y is continuous. We employ linear regression as opposed to something like just correlation when we assume that one of the variables, which we call the dependent variable, is determined by or dependent on a second independent variable. We tend to call the dependent variable y the independent variable x. And we make the assumption that the reverse is not true, that there's not that dependence. If we were just interested in the association of 2 variables where one is not a natural independent and another is not the natural dependent, we might want to do something like correlation, something like Pearson's correlation. And you can actually do both of those things simultaneously. They're directly related in terms of what you end up with from the analytic methods. Things like blood pressure and age, supplement dose and birth weight, are examples of when something like linear regression could be used. Notice when I say dependent on, I don't necessarily mean caused by, although you can mean caused by. In its most basic form, assuming we only have one independent variable, We have simple linear regression, and notice what we have here is the equation of a line. It's just the equation of the line, mx plus b. Everyone remember that from algebra? M is rise over run, the slope of the line. B is the intercept, where it crosses the y-axis. And so we fancy it up a little bit with these Greek letters, beta 0, which is the intercept, where this is what we would expect the outcome to be if x was equal to 0. So it's where the line crosses the y-axis. And beta 1 describes, as x is changing, how does y change? So it's the slope. And then we're not in algebra now. We're looking at probabilistic relationships, meaning there's going to be some noise around the line. People will deviate from this overall average response by some degree, just simply because of a function of their inherent characteristics. So we have to incorporate these error terms in order to make the line fit and the methods work. And again, when you have a single predictor, you call that simple linear regression. When you have multiple predictors or multiple independent variables, like x1, x2, x3, that's called multiple linear regression. But they're doing the same thing. I'm going to demonstrate regression through simple linear regression because it's easier to visualize. So again, y is our response or our dependent variable. X is our independent or explanatory variable or predictor. Beta 0 is the expected value of y when x is equal to 0, because if x is equal to 0, this goes away. The beta 1 goes away. Beta 1 describes the slope, either increasing or decreasing or flat. And epsilon is just everything else left over, which we just lump into an error term. As an example, there's an anthropomorphic kind of study on Nepali children here. This is a real study taken from a very old reference. But they were interested in the relationship between average arm circumference and height for some reason. So the way that you would fit this in a tool like RStudio, there's a function called LM, which just stands for linear model. A linear model is just a linear regression. And you have your response, your dependent variable, and then a little tilde, and then just list out your predictors. Here we only have one. So x is height, y is arm circumference. We have 150 observations. And notice the individual children are from birth to 12 months old. We use linear regression here as a potential option because it allows us not only to look at the association between these things, but also to describe the relationship. We can get an estimate of the average arm circumference or the average dependent variable for each value of the independent variable. We can also describe, as one is increasing, how the other increases. Then one of the assumptions of linear regression is that we have to make sure that a line actually reasonably describes the relationship. If you see some kind of curvilinear or kind of quadratic function, you probably don't want to describe it with a line. There's another type of relationship. So we can look at a scatter plot of the data. Here we have height on the x-axis and arm circumference on the y-axis, and it seems reasonable here to assume that a line could describe this relationship. We can estimate that line using the LM function in RStudio. There are also tons of other software packages that you could use, but the estimate that we're going to get out is of the form of the equation of a line, and we're interested in these two parameters that help us describe the relationship between the average arm circumference, which is y, and then the predictor, which is the height of children. So when we fit this using that LM function, we can end up with an equation of the line where the expected or average arm circumference, y hat is this red line, can be described as a function of the height of children. But I have to take the height, multiply it by the slope, and add 2.7. 2.7 again represents where this line would cross the y-axis at x equals 0. Notice x equals 0 isn't even on my figure, because what is x? X is the height of children. And that it's meaningless in this case. And very often, the 2.7 or the beta 0 here would be meaningless. We just need it to fully specify the line. One of the things that we can use this equation of the line for is to estimate what the expected response will be for individuals with a particular value of the independent variable. So if I wanted to estimate the the arm circumference for children who are 60 centimeters tall, I just plug in 60 for X, and I can say that the expected or the average arm circumference for individuals who are 60 centimeters tall is about 12.3 centimeters. The way that we interpret the slope, that beta 1, it's the average change in Y for every unit change in X. So it's the average difference in arm circumference for kids who are 1 centimeter different from each other in height, which is what I've stated here, the mean difference. I can multiply it out. If I want to do units different than 1 centimeter, I can multiply it by 10 and get the average difference in arm circumference for two groups of children who differ by 10 centimeters. And so it's just the beta 1 times 10. And so for the interpretation for this study, it's 0.16 centimeters. That's the average difference in arm circumference for those two groups, where one group is 1 centimeter shorter than the other. That's not always meaningful. You might want to compare specific groups that are different than 1 unit apart on the X. So maybe 50 versus 60 centimeters. And I just take that difference and multiply it by the slope estimate, and I get 1.6 centimeters. So the average difference in arm circumference for children who are 10 centimeters difference in height is about 1.6 centimeters. The key here, though, is we cannot extrapolate when we use regression methods. Our results from a regression only apply to the range of the observed data. So in other words, what would happen if I extended this study to children who are bigger than 12 or older than 12 months? I would probably get children whose heights in centimeters were larger than what I actually observe in this study. But the key here is I didn't do that. I didn't observe those children, and it could be that I end up with this line might reasonably describe it for a while, but it might flatten off. And there's no way of knowing if the line really applies beyond the bounds of the observed data. And then the intercept in this case is meaningless because the intercept is the expected value or the estimate of the dependent variable when X is equal to 0. And X is equal to 0 is not meaningful here. And in addition, we actually didn't observe it, so it would be extrapolating anyway. When we do inferences using linear regression, what we're actually hypothesizing is that there's an association or that they're independent. If there's an association between X and Y, then we should see a cluster of observations where if I know what X is, I can be reasonably guaranteed that I'd know a range of Y. For instance, if there's a positive association, then I know for small values of X, I should probably be getting smaller values of Y. For large values of X, I can assume that I'm going to get large values of Y. So in other words, there's information about Y contained in X. That only occurs when that slope parameter, that beta 1, is non-zero. Think back to the equation of a line. If the slope of a line is 0, I just have a cloud of points, meaning that if I have a small value of X, I could actually have both small and large values of Y. If I have a large value of X, I can have both small and large values of Y. There's no information about the dependent variable that can be gleaned from the independent variable. So they're not associated. They're not correlated. They're independent. So when we do this, the null hypothesis is actually that the slope is equal to 0. The slope of the line. So that indicates no relationship or no association or independence of x and y, if you will, if you want to put it in that term. Versus, there are a couple of different hypotheses that you might be after. You might be after a strong positive association, a strong negative association, or just a strong association. I'm not saying the word linear, but the word linear is here because that's an assumption of using this, is that a linear relationship can describe the relationship between x and y. And so depending on your research question, you might be looking at any one of these alternative hypotheses. And just like before with the t-test, that's really either a one-sided test or a two-sided test. The test statistic is a t. It's not the same t we saw before, but it's doing the exact same thing. What I observed in the data versus what I would expect if there's no relationship, and that t will measure that. The bigger the t, the more evidence we have that there is an association. In linear regression, I've mentioned before, we actually might have more than one predictor, and actually this is often the case. It's harder to visualize, but the context is the same. So when I have multiple linear regression here, notice I have a single intercept still, but I have a bunch of slopes. And those slopes are doing the exact same thing. They're describing the relationship, how I expect y to change as I change that predictor. The only difference here is when I have multiple linear regression, I have to put a little star next to what I say about any one of these individual slope parameters. What I have to say is that, for instance, beta 1 is describing the expected change in y when I change x1, holding all other features, x2 through xk here, constant. So an example in the form of a regression model where the outcome is birth weight of babies, and I'm looking at two different factors. I'm actually interested in the relationship between the dose of a supplement, which is x1, and birth weight, but I have to account for other things that impact birth weight, like gestational age, that's x2, and gender of the baby, that's x3. So if I fit this equation to my data, and I want to interpret that parameter of interest, beta 1, I can't just say that as I increase dose from dose level 1 to dose level 2, or by 10 milligrams, or whatever the unit is here, I can expect birth weight to increase by beta 1 units. I can't say that. I actually have to fix all of the other factors in the experiment in order to interpret that. So I have to say, among babies who are the same gender and the same gestational age, I can expect for every 1 unit change in the dose, a birth weight increase of beta 1 units. Does that make sense? So you have to, in the context of an experiment, you assume among female babies only who were born at full term, beta 1 can describe the relationship between their dose that their mother received and the birth weight of that baby. Which gets at the assumption of a model like this, that there's not a differential treatment effect for the different sexes of babies. In other words, what I'm saying is, maybe for male babies, the relationship between dose and their birth weight is different than it is for female babies. It's possible. Does anyone know what that thing is called in the context of a regression model? When you have the treatment effect actually being a function of another factor in the experiment. The relationship between dose and birth weight, let's say it's very strong and positive for female babies or for male babies, but it doesn't exist for female babies. What is that called? An interaction. So I'm assuming here something called additivity, which very often in medical research is a very strong assumption. What I'm saying is the treatment effect is totally independent of the gestational age of a baby, meaning babies who are born preterm versus babies who are born full term. The relationship between the dose they received and their birth weight is exactly the same in those two subgroups. And that might not be a reasonable assumption to make. For male and female babies, it might not be the same. So actually including interaction terms will allow you to test formally whether or not the treatment effect is different in males and females for preterm versus full term, and so forth and so on. When you're interested in describing the relationship between a binary outcome, so Y now is no longer gestational age. Now maybe Y is whether or not an individual responds to treatment, whether or not they die. Then we apply logistic regression. Notice this is the functional form of logistic regression, and it looks a lot different than linear regression on the left-hand side, but it looks identical to linear regression on the right-hand side, because the only difference between the two applications is the outcome. So whereas before we were modeling like the average response for babies who are male and full term and who received dose 1, now I'm modeling the probability that they will respond. So don't get into the math here. Just know that I'm modeling the probability of the outcome of interest here. This is the odds. Yes, that's the log of the odds of response. Logistic regression, the data itself, the outcome, is a 0 or a 1. And what I'm trying to do here, notice I have obviously an association between the x-axis, which is temperature, and the y-axis, which is a yes or a no. A 0 indicates the event didn't happen, and a 1 indicates the event did happen. And I'm trying to find a cutoff point of temperature that would very easily predict whether or not someone, in this case, this is not someone, this is a NASA example, so it's not biostatistics, but you could think of it the same way. Whether or not someone will not respond or they will respond. There's some point at which I could be kind of predictive of this relationship. And we do that using this line, acknowledging that the probability of response, which is what's on this y-axis here, notice as I increase in temperature, the probability of individuals responding when the temperature is really low is basically 0. The probability of response is really high when the temperature is high. But there's kind of some fluctuation, right? Some people whose temperature, their X is 30, some of them don't respond, some of them do. And that's where you get this kind of curve relationship. So it's increasing, but it flattens off. And that's why it's a little bit different to interpret. But the idea here is we use odds ratios because we're modeling the log odds of response here. So let's do a quick example. If you ever see a logistic regression model being employed, this is how you would interpret the output. If you use logistic regression yourself and you get output, sometimes you get output in the form of these beta zeros and beta ones, which make no sense. But I'll show you a way that you can actually modify them for interpretation. So here we have a model that's describing the relationship between treatment and death, let's say within 5 years. The treatment is either the experimental therapy or some standard of care, and the outcome is they either died or they survived. So what I'm modeling here is the odds of death. I'm doing it using don't worry about the log transform, but it's the log odds of death as a function of treatment. So let's suppose I fit this model to the data, and I get that slope parameter, beta 1. I get it out of my statistical software, and it says beta 1 is minus 0.69. And you want to write this up for a manuscript or an abstract, but you have no idea what negative 0.69 is. Well, it turns out because of the form of the model, all you have to do is exponentiate that. E to the negative 0.69 is actually interpretable. That is the odds of dying. So if you exponentiate this, you get the odds ratio relating treatment to the probability of death. So if I know that my reference group is the control, and I exponentiate my slope parameter, I get 0.5, which says when treatment for patients involves this intervention, I actually am in the odds of dying. Oh, hold on. Oh yeah, see, I'm comparing it to 0, even in my own mind. Yeah, the odds of dying decrease by 50%. How do I know they decrease? Again, I'm working in ratios here. So a ratio value of 1 would indicate that the odds are the same in both groups. If I have a ratio value less than 1, I'm actually showing a decrease so that the numerator of the fraction is smaller. The odds in the treatment is smaller than that in the control. So values of this exponentiated beta 1 that are less than 1 indicate, in this case, reduction in death. And the reason I know it's 50% is because 1 is where they're equivalent. And I'm 1 minus this value tells me how far away from 1 I am. So it's in percent or fractional decrease of 50%. Another thing that I can just verify in my own mind when I'm trying to write this up is, does it make sense? If I had a negative sign in my original beta 1, my slope, that tells me that there's a negative association, right? That the odds of death actually decrease in the intervention relative to the standard of care. But again, the type of decrease that you have is very difficult to interpret unless you exponentiate that value. What if I fit this data and I got a beta 1 of 0.41? Well, now that I know what that beta 1 means, I know there's actually increasing risk of death because this is a positive value. But before I can understand or interpret how the risk of death is increasing, I actually have to exponentiate it, and I get 1.5, which again tells me now I have a 50% increase in the odds of dying in the treatment relative to the standard of care. And the reason it's 50% is because I'm 0.5 above 1. Before I was 0.5 below 1. Does everyone understand how I got that 50% in both of those cases? Now, that was easy when we were comparing two treatments, but sometimes we apply logistic regression when our predictor variable is not categorical. It's not a treatment versus a control. Maybe we're really interested in the relationship between a continuous predictor and the risk or the odds of death. And so the odds ratio there is a little bit different. The interpretation is the same, but we have to be a little bit careful about how we talk about the odds ratio. It'll be very similar to how we talk about the relationship in linear regression that we had before, where we had the height of a child being a continuous predictor. So here we have X is age and Y is the probability of death. And again, we're modeling the odds of death. Suppose we fit the model to this data and we get an estimate of beta 1, which is the slope, in that model of 0.095. So I know there's increasing risk because it's positive. But it's actually a kind of close to 0, so there's not a huge increase in risk like we saw before, because this is 0.095. It's almost 0. So what does this mean? Exponentiate it, we get the odds ratio that relates age to the probability of death. So if I exponentiate that, I get 1.1. And the interpretation here, just like in the linear regression that we had before, is for every 1 unit increase in the predictor, the odds change by that value. So since I measured age in years, it's important to know the units of measurement. If age was in days, it would be a very different interpretation. But age in years, for every 1 year increase in age, the odds of dying increase by 10%. There was a typo. Increase. Copy-paste error. That should say increase. For multiple logistic regression, we apply it in the exact same way as we did multiple linear regression. And again, we're not talking about the expected birth weight. We're talking about the odds of death or the odds of the event. But we have to account for, again, before we had to say among female babies who are full term, beta 1 describes the expected change in the response for every 1 unit change in the predictor. Here it would be the expected change in the odds, either increasing odds or decreasing odds. So it's the exact same thing, but we have to hold those other variables constant in our statement. Cox regression is where we're going to end. Cox regression is a set of regression models that are very similar to what we just saw with logistic regression. They're modeling whether or not an event is happening. But again, Cox regression is also attempting to incorporate the timing of the outcome in the modeling. So there's actually a combination of two things that Cox regression can detect. They can detect a difference in the fraction of individuals who will have the outcome, yes or no. And they can also detect differences in the pattern of the timing of outcomes occurring. You might actually end up with the same number of subjects in both groups having the event. 40% in treatment A, 40% in treatment B. But the pattern could be very different. And Cox regression will detect that, logistic regression won't. Logistic regression will compare 40% versus 40%. Cox regression will also account for the fact that maybe in treatment A, all of the deaths occurred early. In treatment B, all of the deaths occurred late. And so it can detect that difference even when the overall death rates are the same, which is why it's a little bit more powerful tool than logistic regression because it incorporates more information. This gets back to week 1 when we talked about how much information is contained in the data source. We talked about incidence but let's talk about the difference between hazard ratios and odds ratios. The hazard ratio is a ratio of incidence rates. The odds ratio is a ratio of proportions. So incidence rates, the rate of incident cases over the time period. Proportions is basically like prevalence. It's how many people had this condition or had the event in the time period. And I talked briefly about the difference between how logistic and Cox regression differ. Logistic is estimating the odds ratio. Cox is estimating the hazard. And again, hazard incorporates that timing as well as whether or not the event occurs. Back to our discussion about interaction. We talked briefly about the interaction, the potential interaction between something like the sex of a baby and the dose that they receive, that their mother receives of a supplement, and their birth weight. And then we said that if the effect of treatment differs by that other factor, in that case it was the sex of the baby, then we have an interaction. Cox regression makes the assumption that you don't have interactions. And the specific interaction that you can't have is treatment effect and time. It assumes proportionality. In other words, it assumes that the treatment effect happens early and is maintained through the entire study period because it's called Cox proportional hazards regression. What sometimes we have, and actually I would say probably a lot of times what we have, is a treatment time interaction, which results in the treatment effect being a function of when you observe it. If you observe it early, it might be bigger than if you observe it late. And so a converging or diverging Kaplan-Meier curve is just demonstrating that you have non-proportional hazards or a treatment and time interaction, which means you need to include time as a covariate in the model. So sometimes you'll see time varying covariates. Does everyone kind of remember this terminology from the literature? Treatment here would be time varying. The treatment effect varies as a function of time. So again, there are extensions to survival regression methods where you can take into account time varying covariates. Whether it be the treatment itself, it could be the exposure that varies over time. Cox regression is what's called semi-parametric. It's a combination of non-parametric and parametric methods. but it can accommodate both discrete and continuous measures of event times. It can accommodate multiple independent variables, multiple predictors, and it's also easy to incorporate time-dependent covariates, which is what I just mentioned. As an example of a time-dependent covariate, this is actually the exposure, and this happens a lot in studies where there might be it might not be the factor of interest. In this case it is, but it could be some other factor that actually changes in our study subjects over time that's also going to have some kind of impact on their response. Here we have an example in oral contraceptives and stress fracture risk in women athletes. So there's a study done looking at the effect of taking oral contraceptives on the risk of having this stress fracture over a period of 2 years. The problem is this treatment, if you will, this exposure, can actually switch for an individual over 2 years. Women might be on birth control, go off birth control, go back on birth control over some study periods. They have a mixture of exposures. So if you just examine the risk of the stress fracture by a woman's status at baseline, you might actually miss any meaningful effects of oral contraceptives because you have a mixture of exposures in both of your treatment groups. Women who maybe were unexposed at baseline at some point were exposed. So you can actually, in some of these models, incorporate the times that women start and stop, or that are exposed and unexposed, in order to get a better picture of the relationship between exposure to this and the risk of stress fracture. In summary, the regression methods that we've discussed today allow us to adjust or account for other factors when we're comparing groups. Linear regression compares the means or expected responses of different groups. When you have y is continuous, your outcome is continuous, and maybe you want to adjust for other prognostic factors in the relation, or confounding factors. Logistic regression does the exact same thing, but it's comparing odds or proportions or response rates when you have a binary or categorical, and I didn't discuss ordinal regression, but there are methods whenever your outcome is ordinal as well, like in the case of the tumor response data from complete response to failure. And then Cox regression in its most fundamental form is comparing the risk or survival when y is time to an event, but it's assuming that that risk is steady over time, that it doesn't vary by time. There are extensions to Cox regression when you have a treatment time interaction, which is the same kind of extension that you would have in linear or logistic regression when it's possible that your treatment effect is a function of some other factor in your study. Any questions? We have 10 minutes or so. If there are any other clarifications or questions or comments that you all want to have. Anything to go back over? Okay. You don't have to assume that the hazard in a group is constant. What you're assuming when you have proportional hazards is that the risk is changing in the exact same way. In other words, you see a very early difference, and that difference is maintained. So the difference is constant, not the hazard itself. So you could say the hazard ratio is constant, right? If I calculated the hazard ratio at 1 week, 4 weeks, 10 weeks, at specific time points, which I can do, by the way, then that hazard ratio, it might differ a little bit, but it's for the most part telling me the same thing. If I have non-proportional hazards, then I have the risk changing in one group very differently than it is in another group over time. So I might calculate the hazard ratio at 4 weeks, and it's 1.5. At 12 weeks, maybe it's 1.2. At 20 weeks, maybe it's 1, which tells me there was an early difference that was kind of diminishing over time. So I don't have proportional hazards. You absolutely need to run, yes, you need to take a look, visualize, and make sure that you've met the proportional hazards assumption. There are formal tests for determining whether or not you have proportional hazards, but I would say for the most part you can probably look, if you have, again, a large enough sample size, you can probably look at the Kaplan-Meier curves and see whether or not you're in violation of that. If you have an effect early that goes away, no effect, and all of a sudden you see one, if you have lines that cross, that's the most obvious. But I can tell you if your lines are crossing, unless eventually they separate, then there's going to be no method that will find a difference because you have, different treatment effects that cancel each other out over time. Yes, so one of the causes for that could be like changing exposure. So like in that oral contraceptive example, you might have had people's exposure changing over time, and if you account for that, maybe then you would start to see the pattern emerge, the relationship emerge, but you couldn't see it because it was confounded by changes in exposure over time. Make sure that we don't have any questions online. Doesn't look like we do. Any other questions or comments? I actually took some stuff out because I thought we would go over time, but I must have flown through it this time. I would encourage you to go to our webpage and evaluate the course. I try to use that information each year to take out topics or add topics in. I also like to keep track of where people are coming from, who's interested. That way I make sure I understand who to give the information to next year to get the word out. And also at that webpage, today's the last lecture, so I will be sending that to Dinesh once it processes, and he'll put that up. So at any point in the next year, before next July, you'll be able to view any of these lectures, and you've got all the PowerPoints. So feel free, if there's something that you need to clarify, just send me an email and I can help you walk through that. All right, well, thank you all for coming. You guys deserve gold medals for sticking through 4 Friday mornings.